In this video, we will derive the limiting distribution for the test statistic in a very simple model, and this for 3 different cases of the error distribution. Now, these 3 cases are very important and will pop up in all remaining lectures of this course. So these cases will be the most important building block for all upcoming lectures. Our first case will always be the most simple setting with IID errors. Then we will allow the error terms to be serially correlated. And there are 2 ways that we will correct for these dynamics. Either by adding lags to the model or by using the so-called long-run variance. And we will look at each of these cases now in detail for a very simple model. Namely, the pure location model over here, where we regress yt on a constant and the error term ut with 0 expected value. Now, the estimator of the constant c is, of course, just the sample average of y, denoted here by y bar capital T to denote the dependence on the sample size capital T. We know that our key expression is the difference between our estimator and the true value blown up by root T. Now we plug in here our estimator, the average of y, and then we can further plug in our DGP in red, where yt is nothing more than the constant c plus ut. And then the sum simplifies to this expression over here. We have t times the constant and a factor 1 over t in front. We have 1 over t times the sum of the ut's and the constant c. So the constant cancels out, and I'm only left with the sum of the error terms with a factor 1 over root t in front, since I have root t here in the numerator and t in the denominator over here. So the test statistic for the null hypothesis that c is equal to some value c naught is then given by the difference between the value of the estimator and the value that we lay out under the null, divided by the standard error. And this expression can be alternatively written down like this, where I bring root t here to the top. Now, our goal is to obtain the asymptotic distribution of our test statistic such that we can do inference. And to obtain that, I've summarized here the roadmap of steps to follow. As you can see, the details of the roadmap are not filled out, since the expressions will, in the end, depend on what the error process ut precisely is. But I can already summarize the key steps on this slide. In essence, we need to derive the limiting distribution of the numerator of our test statistic and the probability limit of the denominator. When we develop the numerator, we first write it in terms of our error terms, ut. Note that this rewriting does not depend on the expression of our process ut, and we actually already derived this expression on the previous slide. Next, we need to further write out the scaled average of the error process ut, which will depend on what ut is. And then we will establish the convergence result for the numerator. Then we continue with the denominator. Again, we start by writing out what the denominator is, namely the variance of the residuals, and we derive its corresponding probability limit. In a last step, we can then put all the pieces for the numerator and the denominator together and rely on the continuous mapping theorem to derive the asymptotic distribution of the test statistic. So let's first have a look into the case when the error terms are IID. And I want to reserve the notation epsilon t for IID errors. So I just write down here at the top that my error term ut is equal to epsilon t, so the IID errors. Then the numerator of my test statistic is simply equal to the scaled average of the IID errors epsilon t. And I know from the classical central limit theorem that this goes to a normal distribution with mean 0 and variance sigma squared, assuming that the errors have a finite variance. Okay. Now, what is the expression for the sample variance of my residuals, namely the denominator? I just start from the standard definition, and then I plug in the DGP that YT is equal to the constant C plus, in this case, my IID error. And then I just expand. I have here the squared error terms. I have the square terms for the C, and I have the cross product term over here. What I will then typically now inspect is the stochastic order of the different terms that are involved to see which term is the dominant one. Now remember from before that this guy over here converges in distribution, and that means that it is big OP1, as we've seen in an earlier video. Alternatively, then, the difference here is big OP of order t to the power minus a half, since I need to divide by this power of t in order to get the limiting distribution. Indeed, I need to alternatively blow it up by root t in order to get the limiting distribution. I also have its square popping up over here. So that's why this one is big OP of order t to the power minus 1. What else do I know? I also know that this guy over here converges in distribution. I've written here the limiting distribution at the top of the slide. So this guy is big OP1. It converges in distribution. Alternatively, with an extra factor 1 over root t in front of it, this term then becomes big OP of t to the power minus a half. I've summarized all of the stochastic orders on the slides. If you want to verify these results yourself and really practice with this, because we will often make use of it as of now. Now, let's inspect all stochastic orders involved, and then you can actually see that if we let the sample size go to infinity, all of these terms become negligible, and only the first term is the dominant one. And we know that this term converges to the second moment of the error terms, which is nothing more than the variance of the errors. So what do we have? The sample variance, of course, converges in probability to its population counterpart, as we would expect. And so then we are also ready with the denominator. So let's put all pieces together in the final step. For the numerator, the central limit theorem tells us that this converges to a normal with variance sigma squared. So what is the limiting distribution of this entire guy? Well, that is nothing more than a rescaled version of the limiting distribution of the numerator. whose limiting distribution we already derived. The continuous mapping theorem tells us that this guy then also converges to a normal distribution where we write the asymptotic variance of the numerator that we obtained before, and we need to pre and post multiply the asymptotic variance of the numerator with the probability limit of the scalar in front of it. So this guy over here. So the probability limit of the denominator, the variance of the error terms. And how does this expression get further simplified? Well, we see that all of the terms with the sigmas cancel out, and we are left with a standard normal, which is, of course, perfectly in line with the results that you should know from the regression framework. Now, the question is, what changes, what happens when the error terms are serially correlated? And let's say that we assume that they follow an AR1 process. Now, since the AR parameter rho is smaller than 1 in absolute value, we can rewrite UT that follows an AR1 as a linear process, so as an NA infinity representation, where the NA coefficients are given by the powers of the AR parameter rho. We've seen this in the first lecture week. And using our compact notation from linear processes that we've introduced earlier this week, we can define this here through the lag polynomial notation. Now, which decomposition was crucial to analyze linear processes? Well, that was the Beveridge-Nelson decomposition. And I will also make use of this decomposition now. I start with developing the numerator. So we will rewrite UT here as the product of the lag polynomial and the error term epsilon t, which are IID. And then the Beveridge-Nelson decomposition tells me that I can further rewrite this in terms of C1 times the error term and the difference of a new error process epsilon t. And I use this Beveridge-Nelson decomposition since it allows me to isolate the first term over here from the latter one, which is small op1. Why do I want to isolate the first term? Well, I can derive then the limiting distribution of the left-hand side, making only use of the central limit theorem for IID sequences, the epsilons here. I know that this guy converges to a normal distribution with variance sigma squared, where I just pre and post multiply with the probability limit of the scalar in front of it, namely C1. And what was C1 again? Well, C1 is the infinite sum of the constant terms in the MA infinity representation. So the AR parameter to the power J, and that simplifies to 1 over rho in this case. Okay, so next, I then work out again the expression for the denominator, the sample variance of the residuals. Again, I just start from its definition. I plug in the DGP, where now, pay attention, YT is equal to the constant plus the error UT. I then expand this square. I have the squared term with the U's, I have the squared term with the C's, and I have the cross product term. Verify, like before, that you agree with these stochastic orders, such that it then becomes clear that the first term is the dominant one when we let the sample size go to infinity. And this guy over here will converge to the expected value of U squared, which is in this case equal to the variance of UT, since the expected value of U is equal to 0. Now, what is the variance of UT? Well, UT follows an AR1 process, So we need to compute the variance of an AR1 process. And as an extra exercise in your first tutorial, you were asked to derive this variance, which is again given by this expression over here. So please verify that. Now, what happens if we put all pieces of this puzzle together to derive the limiting distribution of the test statistic? Well, just put the red and the blue pieces from the previous slide together. We know that the numerator converges in distribution to a normal with this asymptotic variance, and we need to pre and post multiply with the probability limit of the denominator. Now, what you first see is that all the variances, the sigma squares, they cancel out. And the numerator can be rewritten like this, such that you can also see that this term over here cancels out with one of the corresponding terms in the denominator, and we're left with this final expression. And we see that now the asymptotic variance does not simplify to 1. So in other words, if we would be using the classical critical values based on the standard normal distribution, we would be drawing wrong conclusions since we don't get the standard normal as a limiting distribution. So our inference would be incorrect when the error terms are serially correlated. So the question then, of course, is how can we correct for this dependence in our error terms? Well, more on that in the next video.